Good day, my name is Wing Pak. I'm one of the instructors in the Civil 1232 course. Today we're going to talk about Phase 2 of the bridge contest, and in the next 40 minutes we're going to go over the purpose of Phase 2, the analysis program which you will be using in Phase 2, ModelSmart 3D, the requirements and specifications which you need to meet for Phase 2, how you'll be graded for Phase 2, how you can create a bridge design in ModelSmart 3D, and finally, ways in which you can improve your bridge designs in ModelSmart 3D. The purpose of Phase 2 is to design the actual balsa wood bridge which you will construct at the end of the term. What you submit at the end of Phase 2 will be the bridge which you build in Phase 3. I'll warn you that if your constructed balsa wood bridge does not match your submitted design from Phase 2, you're going to receive a small penalty. During Phase 2, you can make use of some of the knowledge which you gained from Phase 1. For example, the top chord of your truss, these are going to be in compression. The bottom chords of your truss will be in tension. Depending on the orientation of your truss verticals and diagonals, these may be in tension or compression. Members in compression are subject to fail by buckling. In Phase 1, you were able to get around this by increasing the size of the member or by using a different material type. In Phase 2, this option is not going to be available to you since the only material you'll be using are 1/8 by 1/8 balsa wood sticks. The way you can get around this is to use members which are as short as possible, and also as well for your compression members you can consider doubling these up. We'll explain in more detail what this means later on in this video. In Phase 2 we'll use an analysis program called ModelSmart 3D. This program is meant for educational use only and not meant for real-life design projects or applications. There's actually a big disclaimer when you first start up this program warning you to that effect. Also as well, I want to admit that in terms of this Phase 2, ModelSmart 3D is not as easy to use as that program which you use in Phase 1, Bridge Designer. ModelSmart 3D is actually a lot less user-friendly and it's a lot harder to use. In terms of the specifications for Phase 2, these need to match the actual bridge which you will construct at the end of the term. You'll find these in the Civil 1232 Blackboard course folder. Look under Bridge Contest, then Bridge Design Building Contest Rules and Regulations. Then look under Phase 3. These requirements are: the bridge needs to be constructed of 1/8 by 1/8 balsa wood sticks, which we will provide. The bridge must span between two supports which are placed 600 mils apart. These supports provide only vertical supports to your bridge and nothing in the horizontal direction. The bridge in terms of a dimension cannot exceed 625 millimeters in length. Your bridge cannot exceed 150 millimeters in height or 200 millimeters in width. The bridge must have a continuous opening along the entire length of the bridge. This opening needs to be a minimum 115 millimeters high by 125 millimeters wide. You can imagine that if you have an imaginary vehicle which is this height and this width, this vehicle needs to be able to travel along the entire length of your bridge without hitting any members. Also as well, the bridge must have a horizontal bottom deck along this entire length. The bridge cannot weigh more than 45 grams, which is about the weight of 7 loonies. The bridge must be an overhead bridge, and no parts of the bridge can extend below the supports. So again, what do we mean by this? So again, we have 2 examples shown on this one slide. The first example is an overhead bridge, whereby in terms of all the members, they are above the support level. This is acceptable. The second example below, this is unacceptable. You have members which extend below the level of your supports. One final requirement: in terms of your members, you are not allowed to laminate, to glue together 2 sticks of balsa wood physically together. So here we have a picture to demonstrate this. Along the very bottom, this is not permitted. I have 2 pieces of wood which are physically glued together. This is not allowed in terms of the contest. What is allowed is that you're allowed to double up your members. You're allowed to place 2 pieces side by side, but in terms of the 2 pieces, there must be a physical gap between the 2. Or if you wish, as long as there's no physical attachment or adhesive provided between the lengths between the 2 pieces, that is acceptable as well. How would you be graded for Phase 2? We're going to rank all the bridge submissions from Phase 2 in terms of a load carrying ratio. This is going to be calculated by taking the load carried by your bridge, then dividing it by the self-weight of your bridge. The higher the load carrying ratio of your bridge, the stronger your bridge is pound for pound. The group with the highest ratio is going to be given 100%. The group with the lowest ratio is going to be given 50% for Phase 2. Groups in between are going to be given a prorated mark between 100 and 50%. Later on in this video, we'll go over in detail how you can calculate the load carrying ratio for your bridge design. You can start the program by going to the start icon at the bottom left corner of your laptop. Go into all programs. If you go to a folder called NC NCHAPS, the program is there. On my computer is the second one from the top. ModelSmart 3D. What we recommend is that you save a copy of this, a shortcut of this, to your desktop. You can do this by right-clicking on this icon, selecting the Send To option, and sending to desktop, which will create a shortcut on your desktop. So now let's go to our desktop. There's our icon for ModelSmart 3D. Double click on it to start it up. Initially, the program starts up. Press OK. There's this disclaimer, which I was talking about before, that this program is meant for educational purposes only and not intended for real life prompts. So just press OK. We acknowledge this. Also as well, we created a starter file for you to use with the program. This file makes it easier for you to incorporate double up members in your design. You can find this file once you open ModelSmart 3D. Go to Files, Open Model, go to your C drive, Program Files x86, it's under a folder called, on my computer right now, it's called Pre-Engineering Software Corporations. On yours, on your laptop imaging, it will probably be called PESC. Double click on this. Double click on the ModelSmart 3D folder. Underneath this ModelSmart 3D folder, you'll find the starter file It's called starter file double.members.3dd. So just select that and press open. So now that you opened up the starter file, save a copy of this somewhere on your desktop so you don't overwrite the original master file. You can work with this copy of this file, and this is the one we're going to modify to create your own design. In the starter file, what we have done is that we set the units you'll be working with to imperial units. Even though the specifications are given in metric, we generally find it's easier to work in imperial units and just convert the metric specifications to imperial. Also in the starter file, we have set the extent of your workspace. So where you can find this, if you go to Edit, Preferences, it'll show you the size of your workspace at the upper left-hand corner. There's an X, there's a Y, there's a Z. In the X direction, which corresponds to the length for your bridge, we set this to be 24 inches. The Y direction is the height of your bridge, which we set to be 12 inches. The Z dimension we set to be 12 inches, which is the width of your bridge. To display different views in ModelSmart, you can use different keys on your keyboard. You can use the up and down arrow keys to zoom in and out of your workspace. Left and right arrow keys to rotate your workspace. The plus and minus keys on your number pad to tilt your workspace. 2, 8, 4, and 6 on your number pad to do a horizontal or vertical shift of your workspace. You can also try pressing the function keys, F1 to F9, to display different views of your screen. Also, the properties for a double-up member, we have created this in the starter file as well. If you go to Members, Edit Materials Lists, under Materials 1 is your Balsa D2 doubled property. This corresponds to a doubled-up member. If you click next a couple of times and go to material number 4, Balsa D2, that is your typical member, which is your typical balsa wood, which we would be providing. So Balsa D2 matches approximately the balsa wood which you'll be using. So this member type you're going to use for your typical 1/8 by 1/8 balsa wood sticks. So Balsa D2 doubled, we created so that it has twice the density and twice the strength and compression and tension as the Balsa D2 material. For doubled up members, we're going to trick ModelSmart 3D by creating a single 1/8 by 1/8 member. Then we're going to assign this Balsa D2 doubled material property to it. That way, any members using this doubled up material property will have twice the weight, but it's also going to have twice the strength in tension and in compression as a single 1/8 by 1/8 member. All right, now we're set to go and create our bridge design in ModelSmart 3D. Before we do this, we want to get an idea of the design we actually going to create in ModelSmart 3D. We recommend that you sit down on a piece of paper or in AutoCAD, you draft up and sketch the actual design you're going to create before going to ModelSmart 3D. On your sketch, try to figure out the X, the Y, the Z coordinates for all the joints in your design. For me, the bridge design which I'm going to try to create in ModelSmart 3D is going to be this one here. It's a simple box truss. The height of the bridge is going to be 5 3/4 inches, which is approximately equal to about 146 millimeters. This dimension is from the center to the center of my joints in my bridge. You have to remember that in terms of our balsa wood sticks, they actually have a physical dimension to them. They're 1/8 by 1/8 inch or 3 mils by 3 mils. We need to allow for the thickness of the material at the top and the bottom of our bridge, or another 1.5 millimeters at the top and the bottom of our bridge. If we were to use just 150 millimeters or 5.9 inches as our height, when we actually go and build our bridge, we would actually exceed the maximum height allowed by about 3 millimeters. For the length of our bridge, we're going to use 24 inches or about 610 millimeters. Our bridge is going to be made up of panels of 4 inches in length. In terms of the width of our bridge, we're going to be using 6 inches as a width. With these dimensions, we should be able to accommodate that through opening of about 125 millimeters wide by 115 millimeters high, which we need all along the length of our bridge. I've worked out all the coordinates of my joints in terms of the X, Y, and Z coordinate on my design. These are on this table here. In terms of the height, I'm going to set the base of my bridge to be 1 inch above the origin of the 0, 0, 0 point in my workspace. Why I have done this is to allow me to more easily pick up extra duplicate joints later. Okay. All our members in our initial design are going to be 1/8 by 1/8 members. None of our members to start will be doubled up. This will be my initial bridge design. Over the course of this video, I'm going to take this initial design and show you a few tips on how you can incrementally change the design and gradually increase the load carrying capacity of this design. Alright, now we're ready to create the joints in our bridge. We can do this through one of two ways. The first, we can click on the Add a Joint icon from the toolbar. Then we can left click with our mouse anywhere on our workspace. This will add a joint to our workspace, but the only problem is that it's very hard to control where this joint is located in our workspace. Another way you can create a joint is by going to the menu directly, by clicking on Joint, and then just Add. Okay. So we're just going to left click on our workspace anywhere to create an arbitrary joint. So now we're just going to click with our mouse. As you can see, we created an arbitrary joint in our workspace. Now we're going to try to change the coordinates of this joint. We're going to go to Joint, Properties. We're going to select that. We're going to click on the joint we just created. This brings up a joint property box, which contains all the information about this joint. Included in this box are the coordinates of this joint. So you can see there's X, Y, and Z coordinates. We're going to click on to the X coordinate. We're going to change the X coordinates to 4. We're going to change the Y coordinate to 6.75. We're going to change the Z coordinate to 0. And then we're going to press Apply. So as you can see, the location of that joint physically moved to now the proper location to where I want it to be in terms of my truss. To create additional joints, we can press from this joint property box, this Add Joint button. This initially creates a joint at the 0, 0, 0 location in terms of my workspace. Again, I want to modify this so that this newly created joint corresponds to an actual joint on my truss. I'm going to change the X value of this new joint to 8. I'm going to change the Y value to 6.75. I'm going to change the Z value to 0. This will correspond to the A2 value of the joint, the A2 joint in my truss. Okay, so go ahead, press apply. And now we're going to go through all our joints and create all the remaining joints in our truss on the one side. Make sure when you're creating your joints that you do not create duplicate joints. Duplicate joints, when you have 2 or more joints at the exact location, if this happens, the program's not going to run properly for you and it's basically going to hang. What you need to do at that point is that you need to find and you need to delete your duplicate joints. It's the same is true if you have a joint which is not connected to any members of your bridge. So this is the reason why we basically raise our bridge 1 inch above in the Z direction above the origin. If we accidentally create a joint or an extra joint or duplicate joint, most likely that joint is going to be at 0, 0, 0. By raising our bridge up by 1 inch, it makes that duplicate or extra joint easier to spot and for us to go back and delete. Now that you created a joint on one side of the truss, we can repeat this process for the other side of the truss. But there's a shortcut for doing this, which I'm going to show you. For this shortcut, what you want to do is that you want to create one joint on the other side of the truss. So what we're going to do right now, we're going to create the B1 joint on the other side. This joint is going to be at coordinate location X value of 4, Y value is 6.75, Z value is 6. We're going to use the joint property box just as before. We're going to add a new joint. We're going to change the X values to 4, Y values is 6.75, Z values to 6. We're going to press apply. Next, we're going to go and turn the XY guide plane on. The XY guide plane, just a vertical plane, allows you in the program to work a little bit more easily in terms of the joint locations. So we're going to make sure the XY guide plane is turned on. We're going to go to Guides, first selection, XY guide plane. We're going to make sure the first option's checked off. Next, we're going to move this XY guide plane so it's in line with the truss, with the side of the truss which we just created. We do this by again going to Guides, XY guide plane, move plane to joint, and we want to just basically click on one of the joints on the truss side we just created. Next, we have to select all the joints on this truss side except for that one joint which we already have a duplicate of, this B1 joint. You can perform this joint selection by going to Joint, select the joint, and individually then selecting each one of your joints which you need, with the exception of that duplicate joint at B1. If you make a mistake at any point, you need to basically start from scratch. You need to unselect all your joints and re-perform your selection. Once you selected all the joints except that one where you have a duplicate of, to create the remaining joints on the other side of the truss, you select Guides, XY guide plane, very last option, replicate joints and move plane to joint. Then you select the one single lonely joint on the other side of that truss which you have. created, that B1 joint. So bam, now you see that you created that all the joints on the second side of this truss are created for you automatically. Perhaps at this point, save your work on your computer. Okay, now we're ready to create the members in our bridge. We want to make sure the proper material type and the member size has been set. You can do this by going to Members, Set Default Material and Shape. We want to set these such that the material is set to be material type number 4, a balsa D2. So make sure that's done. If that's not true, just click on this this arrow on the right side and make sure balsa D2 is selected. In terms of shapes, we want to make sure the shape is a 1/8 by 1/8 size member. Again, if this is not true, click on the arrow on the right hand side and make sure that's selected. Now we're ready to create the members. To create the member, you can, through this toolbar, select the Add a New Member icon, or you can go to the menu, go to Members, and Add. To create a member, what you want to do is that you want to left click with your mouse while the mouse button is still selected. You want to drag your mouse, your cursor, to where your member ends and release. For the bottom and top chord members, you need to create all your members such that your members are segmented between the joints. Because you want to do this, otherwise this ModelSmart 3D program doesn't know that that member which you created is connected at a certain joint. So go ahead and create all the members on the one side of the truss. After you're finished, go ahead and create all the members on the other side. Now you want to create some members to link the two sides together at both the top and the bottom of the truss. So go and create some horizontal linking members between the two sides. For the top of your bridge, you also want to add some horizontal bracing along the top deck of your bridge. This will prevent your two sides of the truss from distorting horizontally relative to one another. Along the bottom of your truss, of your bridge, this isn't really so big of an issue because the tension force along your bottom chord members will help to prevent this distortion relative to the two sides. Also, between the two vertical sides, you want to add some vertical cross bracing to keep your two sides vertical and plumb relative to one another. Why do we want to do this? Well, I'm going to say to you that in terms of all the bridges we test each year, about half these bridges fail because the bridges basically lean over in terms of the two sides. You can imagine in terms of the two sides, these are very similar to two pieces of cardboard. In the plane of the cardboard, your bridge is really strong and it's really stiff. In the direction perpendicular to the two sides, there's really nothing or very little to keep your two sides vertical and upright. You can imagine if you make your two sides or you build your two sides slightly out of plumb, this is even made worse. Once you start adding load to your bridge, if you have any initial out of plumbness to your bridge basically starts leaning over and it still fails by this leaning action. Later on in a separate video, we're going to test two almost identical balsa wood bridges, one with and one without lateral bracing, to demonstrate the importance of adding this lateral bracing to your bridge. In this later video, we'll show that just by adding a few balsa wood sticks to brace your bridge laterally, you can dramatically improve the performance of your bridge. In terms of the ModelSmart 3D program, it's not really well suited for checking this lateral failure mechanism or effect. So in terms of the lateral vertical bracing in our models, we're just going to leave that out for now and not model it. In the bridges that you actually construct in phase 3, you're going to actually add these to your actual constructed bridge. In terms of the loading for our bridge, we're going to add 2 vertical loads at the bottom at the midspan of our bridge, one on each side. The magnitude of these loads really doesn't matter. There is a fine braking force option in the ModelSmart 3D program, which will gradually increase these loads until the bridge fails. This matches what we'll be doing in phase 3 of the contest. During the actual testing of the constructed bridges, what we'll do is that we'll take a pail, we'll suspend this pail from the bottom of your bridge at the midpoint. To this pail, we're going to slowly add sand to it until your bridge fails. At that point, when your bridge fails, we're going to take this pail, we're going to weigh it. We're going to determine the weight or the load at which your bridge fails. To apply these loads to your bridge, to your design, go to Loads, go to Set Default Loads in the menu. We're going to change the X value to 0, Y value to -1, Z value to 0. This will set the magnitude of the loads which we'll add to our bridge. Now go to Loads, Add Change Y Force from the menu. Click on the middle bottom joints on each side of the truss. So what we did just now is that we added a load of 1 pound in the downward direction to each side of our truss. Now we're going to add some supports to our bridge. At the one end of the bridge, we're going to prevent the bridge from moving horizontally in the X, Y, and Z direction. In terms of our bridge, we're going to allow joint though to rotate freely. How we'll do this is that we're going to specify what's called an universal joint. We can do this by clicking on the Add Universal Hinge icon in the toolbar and then clicking on the 2 joints on the one side of the truss. And on the other side of the bridge, we want to prevent the bridge, from moving in the vertical direction. In the horizontal direction, we're going to allow it to move freely. We're going to spec on this side of the bridge an XZ roller. We're almost ready to run the analysis. Before we can run the analysis, we need to set a number of options used in the program. Go to Analysis option, select Color Failed Members. This will highlight the members which fail in our model. Also as well, select Consider, then make sure only axial stresses is turned on. So now the program considers only tension and compression forces in our member. It will not consider bending, torsion, or shear in the member. These you may not know what these are right now, and you'll actually learn what these are later on in your construction and civil courses. Next, under Analysis option, make sure that Include Self-Weight is turned on. So now the program will consider the self-weight of your bridge in the analysis. Lastly, under Analysis option, make sure the Fine Braking Force option is turned on. The program will automatically now increase the vertical load of -1 in the vertical direction we just added until your bridge fails. Now we're all set to run analysis in the ModelSmart 3D program. Select Analysis and then run the analysis. The members which fail first are highlighted in red. For our design, the bridge fails at the end diagonals. So if we go to Analysis, Global Data, you can find the load at which the bridge fails and the weight of your current design. So right now, for this design, our bridge weighs about 23.8 grams or about 0.052 pounds, and the bridge fails with a total vertical load of about 9.2 pounds. In terms of our load carrying ratio for this design, we can calculate this by taking 9.207 pounds divided by self-weight of 0.052, which gives us 177. So the load carrying ratio for this design right now, it's 177. If you select Analysis, Member Results, then click on one of the failed members, you can actually see detailed information on that member. So let's do that. You'll see that for one of the members which failed, the length of that member is about 7 inches. In tension, this member, using this balsa D2 member material property and this 1/8 by 1/8 size material, that member in tension is good for about 50 pounds according to this program. In compression, the members is good for an estimated 2.86 pounds. Looking at the mode ratio for the axial force, this is about 1.001. This mode ratio is a ratio of the actual force in the member versus the member's capacity. So therefore, for this member, the program's telling us that it's overloaded and that the member size which you use is no good. So how can we improve this design? Without changing geometry, there's really very little we can do. The only option available to us is that we can double up some of the members which failed. So we could try to double up some of the failed members from our last run. So go to Members, go to Set Default Material and Shape. Instead of the material being type 4 balsa D2, we're going to change that to a balsa D2 doubled. We're going to leave the shape as a 1/8 by 1/8 member. Press OK. Now to change the member properties of the 4 members which failed, we're going to go Members. We're going to go halfway down in terms of this menu, change material. Then we're just going to click on the 4 end members which failed. This will change the 4 end members at the end of our bridge from single members to a double up member. So now let's rerun our analysis. For this new design, our bridge weighs about 25.9 grams or about 0.057 pounds. The bridge fails with a total load of about 16.9 pounds. In terms of a load carrying ratio, it is about 296. This is about a 70% improvement over our previous design. So let's continue and try to improve our design. Let's try to continue doubling up some of the members which failed from our last iteration and see if there's an improvement. Under Members, make sure Change Material's been selected. We're going to select the top chord members which failed in our last run. Let's rerun our analysis. The bridge now fails at 4 of the middle vertical members. Right now our bridge weighs in at about 27.1 grams or about 0.059 pounds. In terms of a load, at failure, the total vertical load at failure is about 17.1 pounds. For a load carrying ratio, you can calculate this by taking the 17.14 pounds and dividing it by 0.059 pounds, which gives you about 291 as our new load carrying ratio. So as you can see, our load carrying ratio has actually gone down. So in terms of performance, the last set of changes we made actually made the design worse and not better. So if we were just locked into this one particular bridge geometry and nothing else was for play except for the sizes of these members, whether they're doubled up or single members, what we should be doing in terms of optimizing this design is that we should be just doubling up the end diagonals. For this bridge design, we've pretty much done all we could in terms of improving the load carrying ratio. Now we need to start looking into changing the actual geometry of the bridge, or to look at a different bridge configuration. All right, I think I gave you enough information and tips, so now that you can confidently go ahead and create and analyze your own designs in ModelSmart 3D. Now it's your turn to go ahead and create some bridge designs on your own. With that, I'm going to sign off. I hope that you learned a lot from this video and that you picked up a lot of good tips, and hope that you will have a lot of fun with this second phase of the bridge class.